Hello, everybody. Today I'm going to read a paper about the topic vehicle tracking and speed estimation under mixed traffic conditions using YOLOV4 and source, a case study of HANOI. And this paper presents a method to estimate vehicle speed automatically, including cars and motorcycles under mixed traffic conditions from video sequences acquired with stationary cameras in Hanoi City of Vietnam. The motion of vehicles is detected and tracked along the frames of the video sequences using YOLOV4 and source algorithms with custom datasets. In the method, the distance traveled by the vehicle is the length of virtual point detectors, and the travel time of the vehicles is calculated using the movement of the centroid over the entrance and axis of virtual point detectors. For example, region of interest, and then the speed is also estimated based on the travel distance and the travel time. The results of two experimental studies show that the proposed method has small values of net within 3%, proving that the proposed method is reliable and accurate for application in real-world fixed mixed traffic environments like Hanoi, Vietnam. Vehicle speed is fundamental parameter for traffic flow into macroscopic and microscopic traffic analysis. Vehicle speed has defined as the rate of movement of vehicles in distance per unit of time, and it indirectly or directly related to the traffic state and road conditions. Speed measurement will make policymakers to estimate assessments of the traffic state of the other anomalous events, as well as to implement solutions to deal with the overspeeding behaviors of drivers. Besides, it can be compared with the vehicle counting to assist in traffic planning and signal identification, as well as pollutant emission assessment. Vehicle speed can be measured automatically from various sources such as magnetic inductive loop detectors, radar detectors, infrared detectors, video-based systems, and so on. In comparison to other sources, video speed system has a variety of benefits, including portability, affordability, easy installation, and operation. Regarding the estimation approaches, the estimation of vehicle speeds from the video-based system can be conducted with traditional approaches and deep convolutional neural networks. Traditional approaches commonly used include background subtraction, framing differencing, and optical flow. Background subtraction works pretty well in real time. It is quite sensitive to changes in lighting, weather, and other environmental factors. The frame differentiation approach has a good ability to adapt to changes in light, but it is unable to obtain on the object's priori information. Optical flow may detect moving objects without any prior scenes knowledge, but is inapplicable for the real-time detection due to its intricate and time-consuming calculation. Generally, traditional approaches are sensitive to noise. They are difficult to improve accuracy in complex traffic conditions. Because of their accuracy, CNNs are commonly used to overcome the shortcomings of the aforementioned traditional approaches in intelligent traffic analysis, such as vehicle detection, tracking, and speed estimation. Typical CNNs include region pay CNN, you only look once. For example, Kumail and salt. To estimate vehicle speed and achieve the root mean square errors of 9.54 for estimating vehicle speed in movies or unrestricted traffic. Biswart et al. Applied a system of vehicle speed detection based on the faster RCNN. The feature pays image alignment, the general and spatial reliability tracking, and the structural similarity index measurement. The system achieved a speed accuracy of 96.8%. However, the representations in RCNN and its associated approaches take a long time to run completely on an image. To overcome these restrictions, SSD and YOLO predict objects in images using local information. Hence, they accurately identify objects in real-time image processing while maintaining a high map mean average precision. Besides, YOLO has several advancements: patch normalization, dimension clusters, and anchor passes, leading to high map in the MS COCO dataset. Therefore, YOLO has received a lot of attention recently. For instance, Liu et al. Used YOLO version 2 and FlowNet to estimate a real-time speed of an object. Liu and Zhuang used YOLO version 4 and did sort for detection and tracking vehicles on freeway. Gautam and Mohapatra used YOLO to estimate the speed of an approaching vehicle when this vehicle is to cross the road region of interest using a moving camera. The system achieved an average accuracy of 90%. YOLO has been employed successfully for vehicle detection in homogeneous traffic with four-wheelers vehicles used predominantly. However, most of the research do not focus on vehicle detection and tracking in a mixed traffic flow like in Vietnam, where on-road vehicles are used frequently. For example, in Hanoi, the capital of Vietnam, motorcycle traffic accounts for 86% of traveling in the open area. In contrast to homogeneous traffic like found in developed countries, traffic flow is quite complicated due to the non-link-based movement of vehicles on roads. Hence, the detection, tracking, and speed estimation of vehicles in mixed traffic flow like Vietnam remain a major challenge. In this study, we provide a method to estimate the speed of the vehicles, including cars and motorcycles, under mixed traffic flow using a sequence of video imagery from an uncalibrated camera. The proposed method has used the state-of-the-art object detector and tracking YOLOV4 and stored with a custom dataset for vehicle detection, classification, tracking, and speed estimation. In addition, the average speed of mixed traffic flow is also estimated based on the individual vehicle and vehicle type. The following are primary. Proposing a method for speed estimation under fixed traffic flow. Designing a custom dataset for YOLO version 4 and sought to track and estimate vehicle speed. As experimental studies show that the proposed method is practical and easy to use. The remainder of this paper is organized as follows. The proposed method employs YOLO version 4 and source is described in section 2. The experimental study estimates vehicle speed in Hanoi City, Vietnam is described in section 3. The conclusion and future work are provided in section 4. Workflow proposed methods. The proposed method of vehicle tracking and speed estimation includes main three components: vehicle detection and classification, vehicle tracking, and speed estimation. In the following session, we provide detailed explanation of its component. A flow chart of the proposed method is shown in the figure 1. Vehicle tracking and speed estimation. Input image detection and classification, tracking association, speed estimation module. To detect and classify vehicle in traffic video, we applied with a custom dataset. To implement a real-time vehicle detection, YOLOV offers improved accuracy and quicker results in comparison with above-mentioned CNNs. The architecture of the vehicle detector using YOLOV consists 4 components as follow: input image, backbone network, head, and neck. The backbone network is a pre-trained network from the input images and expressive features based on the CSP darkness for 53 architecture. The head of YOLOV4 consists of spatial parameter pooling, path aggregation network, and YOLOV3, and this is utilized to predict the classes and bounding passes of the vehicles and enhance the training speed and the model accuracy. The next is to increase strength by collecting feature maps from the intermediate stages. Besides, the greedy non-maximum suppression is utilized to ensure that there are no overlap in the proposed area. In your version 4, the input image is split into a grid as multiple as with its grid self class of the vehicle detection. We take B bounding passes and place one in its grid cell. The network then outputs an offset value for the bounding pass and class probability. Here, the bounding passes are chosen and the vehicle in the image is then located using those that have a class probability with a particular threshold. Alright, you look at the MS Coco dataset provides a fair inference speed and relatively high performance. Bicycle, motorcycle, cars, bus, trucks in the MS Coco dataset are road transport modes. In the particular application with complex traffic context like Vietnam, usually capable of identifying and classifying large and medium-sized vehicle, cars, buses, trucks. But is not stable when detecting small-sized vehicle, bicycle, and motorbikes due to the lack of their training data. To overcome that drawback, we have built a real training dataset of vehicles that is taken from the real traffic situation in Vietnam. Cameras are used to collect most of the image from the training dataset placed in front of or behind vehicles and are collected from different real-life scenes on different traffic routes. Some of the images are also taken from the visuals available on YouTube, Google Maps, Street View, and other sources. We have considered 2 main types of vehicle categories for vehicle detection, including motorcycles and cars, which account for 95% of on-road vehicles. Because other vehicle, bicycle, buses, trucks, etc., account for a very small percentage of traffic flow in the open areas, they should not be considered in this story. Our data includes 2,543 images of motorcycles, cars, and other vehicles, bicycles, buses, trucks, etc. The vehicle data is divided into a training set and a validation set with ratio 7 and 3. Okay. Motorcycle, cars. The process of vehicle labeling In its image is done with the help of the label image tool developed by Tusali in the diagram of training process on our dataset is shown. The YOLO layers are trained via YOLO custom configuration file to optimize configurations. Besides this, the YOLO file and the pre-trained network is used for the training model of YOLO. The process of training and validation is done on Google Colab, equipped with a Tesla T4C GPU. The result of the average loss of YOLO version 4 with 33,000 iterations equated to 1.1941. The overall map is 96.55%. The values of average precision of cars motorcycle really high. These values are high and reflecting the capacity of our dataset in vehicle detection in Vietnam transport context. In this session, we briefly describe the simple online and real-time tracking algorithm to track an individual vehicle. SORT is a real-time and online tracking algorithm integrated with the command filter and the Hungarian algorithm, which has an accuracy comparable to the state-of-the-art online trackers were supporting higher update rates. The state space of its vehicles in models as follows, where SY is the center locations of the boundary parts of vehicles, as R represent the scale area, that's the aspect ratio of the boundary parts, respectively, and the velocity element. When detection is associated with a vehicle, the detected bounding bars is used to update the states of the vehicle. The location of new bounding bars for each vehicle is predicted based on the command filter. Regarding data association, source uses the intersection used over union between its incoming detection and on prediction bounding pauses of existing vehicle. The value is used to populate a cost metric, which is then solved by a Hungarian algorithm to assign its track an appropriate detection. In addition, a minimum value of IOUs is applied to reject assignments when the overlap between the detection and the vehicle is less than IOU. The vehicle tracking procedure of sorts is shown. Image file label format state object trained image is label test image 2, image 1, and the image n, and it's labeled. And then coming to the training models with the pre-trained network, coming with a configuration file for training and training validation set, and the outputs with the weights for the YOLO train. Vehicle tracking procedures with source detection, IOU match and match track and match detection and match track. If and match track is with delete and match detection, it will create a new track and then tracks and the command filter predicts and go back to the IOU match. If the match tracks, it will command filter update and update and so go back to the track. For its detected vehicle, the bounding bars is given up to identify and determine the central point of the vehicle, which is the most important thing for tracking and its speed estimation. While the vehicle is in dry region of interest, the vehicle will be tracked and calculated the travel distance using a Euclidean distance. After that, we can estimate vehicle speed between some consecutive frames by a central point. To simplify the calculation, in this paper are all used as a virtual point detector. Vehicle speed is rise is a constant and the travel distance by the vehicle is equal to the length of the virtual detector. The side of the road along the length of the road assessment as so is the figure 6. The speed of the vehicle between the two scan lines, the entrance and exit of right, and can be calculated by the simple equation as follows, where v is the speed of the vehicle that traveled in right. This is t is the travel distance of the vehicle in right. In this study, is the length of the virtual detector, the length of the right. We can take t equal 5 meters. Is t is the travel time in seconds for the vehicle to run the travel distance, and it can be calculated as you see the travel distance in the time spent of travel time is the entrance of the virtual point and the exit of virtual point with the scan line 2 and scan line 1, and with that we calculate with the speed, and we the calculate the time due to large variation in the speeds of different types of vehicles, including motorcycles, cars, trucks, buses, and so on. We can determine the weighted average speeds at the speed of the mixed traffic flow in the observation period using a given equation, where n is the total number of vehicle time with present in mixed traffic flow. Average speed of the vehicle time that is calculated based on the equation and the number of vehicles is time. Average speed of mixed traffic flow, number of vehicles of the is time. In this paper, the performances of speed estimation of the vehicle, motorcycle, and cars are calculated using mean absolute percentage error and the root mean square errors, which are determined as follows. The experimental data and traffic videos are to detect the vehicle's motion and estimate its speed. To evaluate the proposed method, we have carried out two experimental studies corresponding to location in Hanoi city of Vietnam, where we have certain differences in terms of geometric and traffic conditions as well as average speed. The experimental data has been acquired by stationary cameras located at pedestrian bridges on Suntui Road, coordinates longitude, and the Metri Road. The videos they were resolution with 29 frames per second. The first experiment was 1 minute video clip and the other 3 minutes video clip. The experimental studies were established using Python and were run on the Google Colab environment. Vehicle counting calculated with our method and manual methods was the number of vehicles passing the road. The result of vehicle counting was shown in Table 2. Chemical detect and count is in experimental result vehicle detect and counting, manual counting, our method counting, accuracy. Table 2 shows that there are 45 vehicles, this motorcycle and car, static, collectively, and no vehicles. It was misdetection with the first experiment in 20 road. In the second battery were mixed vehicle counting. However, error was quite low, within 5%. The average accuracy achieved in the experimental studies was 97.6%. This is quite a high value, and this allows us to estimate the speed of the vehicle, motorcycles, and cars. The results of speed estimations based on our method and the manual method were displayed in tab 3, speed estimation results. Number of vehicle estimated, average speed for manual observed average speed from our method map risk. So that the number of vehicle estimated internal vehicle speed was lower than the number of vehicles counted in experimental studies, counting for 91% of the total number of vehicles counted. This was because vehicle matching and tracking errors occur due to many noises influencing the order of the vehicle axis. When determining the average speed of the vehicle flow, it is not necessary to determine the speed of the whole number of vehicles through an observation cross-section. Only a sufficiently large sample size is acceptable. Therefore, this value is consistent with reality. Besides, the result for the map are MSE are the proposed method were quite small, within 3% or and 2 kilometers per hour, respectively. These results can allow us to use the proposed method for other related study, traffic status analysis, traffic jam, and so on in the future work. In this paper, we have presented a computational efficient vehicle detection and speed estimation method for traffic videos using mixed traffic flow in Hanoi City of Vietnam. The proposed method was based on YOLO's algorithm in combination with the source algorithm with the custom dataset. The speed estimation results in experimental studies show that the accuracy of the proposed methods were quite high, which made within 3%. However, the proposed methods still have some limitation has been to be overcome certain limitations on the time of vehicles considered limitations on traffic and weather conditions and other aspects. In the next study, we will increase the number of images for a training dataset to increase the time of vehicles such as persons, trucks, etc. And at the same time, to improve the algorithm to increase the accuracy of the proposed model in different traffic conditions in Vietnam. Besides, smartphone applications and real-time processing will also be of actual interest. So